Hey mathletes, here we are looking at proportions in triangles, section 8.4 in our books. So we're going to use these proportions to help solve for side lengths. So first thing I want to do is I want to start looking at simplifying and solving proportions. So remember, as we think about proportions, we want to establish this idea of cross multiplying or cross product. Well, to do so, let's just use some properties that we know about solving equations. So if I want to get x by itself, recognize it's in the denominator, so let's undo division on both sides. So on the left side, I'm dividing by x, so I'm going to multiply by x on this side, and I'm going to multiply by x on this side. In doing so, it cancels out x's here, okay? And then on my right side, I have 2x over 3 equals 8. And then on my right side, I want to do this undo this dividing by 3. So I'm going to multiply both sides by 3 and multiply both sides by 3. So I'm going to leave this as their products, and we'll see that we get 3 times 8 on this side. These 3 cancels out, and we're left with 2 times x. Notice that 3 times 8, sorry, 3 times 8 is this product right here. So that's that cross. And then this other cross, 2 times x, ends up being on the other side of the equation. So that's how we can use that property to help solve out. And so we call this the cross product. So this cross product, if we simplify it here, we get 24 equals 2x. Divide by 2. Divide by 2. I get 12 is equal x. So we're going to use this cross product to solve our proportions, but remember, it's just using these properties of multiplying out to undo our division and then collecting and multiplying out. So let's look at a different one. So if we have a quantity, it doesn't change too much, but let's just go ahead and do this cross here. So I get 5 times x, is 5x, equals the other cross, 3 times the quantity x plus 1. So if I see more than one term, a binomial or trinomial, in a numerator and denominator, I want to make sure that I multiply by the entire thing. So as I have 3 times the quantity x plus 1, I want to distribute that out. So I get 3x plus 3. On the left side, I get 5x. Now solve this like you would any other equation. Subtract 3x from both sides to get all my x's on one side. And I'm going to get 2x equals 3. Divide by 2. Divide by 2. I'm going to get x equals 3 halves, or 1.5. Okay. So next, as we were talking about similar triangles before, we want to be able to complete our similar triangle statement. So on the left side, I have BXA as my triangle here. So as I'm trying to write that similar triangle statement, I'm going to write it as, so start with D, corresponds to B, and then we went to X, so then we're going to go to X here, so BXC is that those are similar triangles. Okay, and in order to solve for our similar triangles, I'm going to look for sides that corresponding that we know. Okay, and we want to give the ratio smaller to larger. So for my small triangle, I can take, let's just go ahead and take our smaller sides. So small to large is 6 to 9. Okay, or we could use this other side, corresponding side, B to A and D to C, and call it 8 to 12. But you should recognize that that ratio, okay, is also reducible. So here, 6 and 9, we can divide by 3. So then we end up getting it's a 2 to 3 ratio. And notice at this point, we should notice 8 and 12 are divisible by 4. So when we divide that by 4, we see we get a ratio of 2 to 3. So that is our similarity ratio of smaller to the bigger triangle. Okay. The followed polygons we want to find for x and y, knowing that they are similar. So that similarity ratio, if we go smaller to big, okay, small to big, I'm going to use these two corresponding sides. Small to big is 8 to 16, or I can say that it's 8 over 16. Okay. Dividing by 8 on both numerator and denominator, I see that this simplifies to 1/2. So that's my similarity statement. Okay. So if I want to use this to solve for my y value, okay, notice 8 is the triangle on the left, and 16 is the triangle on the right. So as I set up my new ratio with 1/2, I want to make sure my numerator and denominator correspond. So my left side, now I'm solving for these corresponding sides. My left side I know is 4, and my right side is y. There's my unknown. Now again, I'm going to utilize my cross product. So I get 1 times y is just y, and 2 times 4 is 8. So y is equal to 8. You can see our triangle is just doubling in size, our length, so 8 to 6, 4 to 8. Okay, now our angle, because they're similar, we know all the corresponding angles are congruent. So if 63 on my right triangle is that top corresponding angle, then I know that x is also 63 degrees because they're similar. Our next example here is a classic example using similar triangles dealing with shadows. So we have a diagram down here, and the basic premise of this is that these measurements have to be done at the same time because the sun needs to be in the same location. Okay, so we have a girl that's 4 feet tall, and she casts a shadow of 3 feet. So you can kind of see I illustrated that here. So at the same time, okay, meaning the sun's in the same position, which means the angle that's created here and with the house and the 90-degree angle is the same as the angle here. And we're also basing this premise on that the idea that this house is, we're finding the height that is perpendicular to the ground, and the ground that the girl's standing on is on the same surface and height as the house, so that they're both standing erect or 90 degrees to the ground, and we're dealing with a flat surface. Okay, so as we set up this proportion, what I like to do is I like to just kind of line up my rows and columns with my proportions. So I'm just going to dictate, let's say on the top, I'm going to say I have the actual height. So, and on the bottom, I'm going to have the shadow height. Okay, and then as I set up my proportion, I want to recognize that the ratios have to be within each one. So on the left side, I'm just going to say this is the girl. And on the right side, I'm going to say this is for the house. So as long as you set them up, you could set them up slightly different and have the house on the left and the girl on the right, and the shadow on the top and the actual on the bottom. But as long as you line up things correctly as you do your cross product, you'll get the same solution. So figure out what I know. So what is the actual height of the girl? Well, the actual height of the girl I know is 4 feet. Okay. So now what's the actual height of the house? Well, that's what I'm trying to find. How tall is the house? So that's my unknown x. Well, the shadow of the girl I know is 3 feet. I know my scale's not to size. I know 4 feet here looks shorter than 3 feet, but hopefully that gives you an idea here. And then the next blank I have is the shadow of my house. Well, the shadow of the house is given as 18 feet long. So now that I have my proportion, it's relatively straightforward to solve it. So I do my 4 times 18, and I'm going to get 72. And then on the right side, I'm going to get 3x divided by 3 divided by 3. And then I'm going to get x is equal to 20. So 3 goes into 60 20 times. I have 12 left over, so I'm 24. And then it's a word problem in geometry, so I should be thinking about units. So I'm 24 feet tall is my house. Okay. So here we are looking at similar polygons. So you can see they're kind of set in corresponding positions. So if I want to set these up, I'm going to try and make sure I'm setting up my ratios. And again, I'm going to identify a mathematician's choice. I'm just always going to make sure that my proportion is my left shape to my right shape. Okay. Then what I like to do is I like to kind of find my key. And the key is one side that I know for both the left and right shape. So this corresponding side here corresponds with this. And I know both those measurements as 8 and 6. So my left is 8, and my right is 6. So I'm going to use this to set up for all my other proportions to solve for x and y and z. Okay. So for my first example here, okay, I'm going to see that I have, I'm going to use 8 over 6. Okay, and I'm going to solve for x. So x is on my left side, and that corresponding side is 12 for my right side. So now as I set up my proportions, I do 8 times 12, I get 96, equals 6 times x, 6x, divide by 6, divide by 6, I get 16 is equal to x. Now, for my z, sees that it corresponds here with 10. So as I set up that proportion, again, I'm going to just stick consistent here and say left side, use my 8 over 6. And now you set up the ratio for the unknown side. So my left one is 10. My right one is z. So now as I multiply this out, I get 8z equals 60. So regardless of the proportion you set up, at the end, you should make sure that you get 8z equals 60. Then when you solve it, you know you're going to get the same solution. So then I get z is 7.5. Okay. And then my last one I see is y here, so that corresponds with 6. So again, I'm going to have 8 over 6. My left side is 6. My right side is y. Again, using my original defined ratio. Multiply this out, I get 8y equals 36. Divided by 8. Divide by 8. I get y is 4.5. Okay, let's look at another example here. So if we're trying to just complete the following statement, so knowing I have a similarity statement, I see m is in the middle location here, so that is congruent or equal to q. Okay, and then ln is my left triangle, and it corresponds ln, and PR is my right triangle, my similar statement. Okay, so as I'm looking at mn, it's these locations on the left. So on my right triangle, that corresponds to QR. Okay, so just utilizing our similarity statement and extrapolating some information from that. Next on 8, we're looking at, can we prove these triangles similar? Okay, so our similarity statements, similarity proofs we talked about, we have angle-angle similarity, we have side-angle-side similarity, and we have side-side-side similarity, where angles have to be congruent or equal, and sides have to be in proportion. So because I don't know two angles, and I don't know all my sides, the only possibility I have is side-angle-side. Well, I have angles that are congruent, H and O, so that takes care of having my angle being congruent. Now I need to show that my sides are in proportion. Okay, so again, I'm going to set up my proportion, and to give you an idea, I'll call it triangle MOR, and I'm going to set up that proportion with triangle GHI, or you can think of it as left and right. So the side that I know, let's test one side. Okay, so that side is MO, so I'm going to use these two. I get 6/3. Okay. For my other side, I have 10 and 4. So 10 goes on top and 4 over here. So my question, if these are proportional and are similar triangles, that these are equal. Well, is that true? Well, I can see that if I cross multiply, I get 24 is equal to 30, and that's not true, so they're not proportional. Or the triangles are not similar. We could also see this another way by just recognizing that our scale factor from big to small is 1/2, because from 6 to 3 is 1/2 there. But that 10 to 4 is not 1/2, so we don't have that similar dilation in our image. So these are not similar. This would have to be a 5 here, right, if we wanted these to be similar triangles. Next, looking at maps. Oftentimes we use maps and scale drawings. We're talking about similar figures. So as we're talking about a map, we can see we have a scale often given in our maps that every 2.75 centimeters corresponds to 4 miles on the map. We're trying to plan a route that from the Horsetooth Reservoir to Horsetooth Rock. Okay, so on the map, the actual distance, or the map distance, is 7.3 centimeters, and we want to find the actual distance. Okay, so what's useful here is, again, I'm just going to decide mathematician's choice. I'm going to decide my ratio. So on the top, I'm going to give, say it's the map, which is in centimeters, and on the bottom is the actual real life distance, and that's going to be measured in miles. So I know the map gives me one of my ratios, so I get 2.75, okay, over 4. Okay. So if I'm using that, I know on the map that it's 17.3 centimeters from Horsetooth Rock to the Horsetooth Reservoir. And I know I put that in the numerator because I'm getting that from the map. And I want to find my actual distance. That's my unknown here. So now I have a proportion set up with one unknown, so I can use my cross multiplying. So when I do 4 times 17.3, I'm going to get, so here, I get 69.2 equals 2.75 x divided by 2.75 divided by 2.75, and I see that I get 25.16 is equal to x. And again, this is my actual, so I need to remember that my units are 25.16 miles as my final answer. Okay, so there's some other theorems we want to talk about here. One is our Sidesplitter Theorem, that if we have a triangle and it's intersected on 2 sides, okay, then that line that's intersecting on the 2 sides is parallel to one of the sides. How it splits this side, TV, and TR are in proportion. So in other words, x over 16 equals 5 over 10. Okay, you could also set it up as x over 5 equals 16 over 10. Okay. Notice on both these, regardless of how you set them up, when you cross multiply, I get 10x equals 80. Okay, and if I do it over here, same thing. 10x equals 80. So either way that you set them up is fine. I usually go with this one because geometrically I can kind of see x over 16 kind of lines up here, and 5 over 10 lines up here, and kind of imagine my parallel lines being equal sign, and that kind of sets up my proportions. So this is usually the way that I end up setting them up. It's just easier for me to see that. So let's apply it, or let's look at another Sidesplitter theorem. So this doesn't work with just triangles. We can again see that with any three parallel lines intersecting two transversals. Okay, so our transversal is here and here. There are three parallel lines. The segments intercepted on the transversal are proportional. So in other words, we can say that A over B is equal to C over D. And again, you can kind of see that's the way that I will usually set them up. Okay. But if you choose, you could also do A over C equals B over D. And again, when you look at the cross products of these, you'll get AD and CB when you multiply them out. Okay. The last theorem here today is the triangle angle bisector theorem that states that if a ray bisects a triangle, okay, so we had triangle ACB, and we bisected it with ray AD, so then we get this angle is congruent to this angle. So that's how we know we can use this theorem, where we see this kind of illustration where we're bisecting that angle. Okay, it divides the opposite side, so this opposite side CD and DB proportional to CA. So how you might want to set this up is saying, like, again, I see CA over CD equals AB over BD. Okay, so let's apply a couple of these. So first, let's find Y here. So I'm going to set up, see this as my proportion. So I get 12 over Y equals 10 over 6. So as we cross product, we're going to get 72 equals 10Y. So dividing by 10, I get 7.2 is equal to Y. Okay, next example here is a Sidesplitter theorem. So we got two unknowns. First, in red, I'm going to solve for x. So I'm going to have 6x over 5. 6 over x and 5 over 12.5. So I'm using these values, and I can just kind of vision that these are my proportions. So I see that. So 6 times 12.5 is 75 equals 5x. Divide by 5 on both sides, and I get 15 is equal to x. My last one here is trying to solve for my y. So I'm going to see it more like this. 6 over 9 is equal to 5 over y. I multiply that out, I get 6y equals 45. Dividing 6 by both sides, and I get y is equal to 7.5. Okay, my last example here. Okay, find the value of x. Okay, so I'm going to have 24 over x is equal to 40 over 30. Okay, so at this point, I like to recognize that 40 over 30 can be simplified to just 4 over 3. So then my multiplication ends up being a lot more straightforward and dealing with smaller numbers that can be easier. So then as I multiply out, I get 72 is equal to 4x. Divide both sides by 4. And I get x is equal to 18. Okay, that concludes our notes today on proportions and triangles. Please bring any questions you have to office hours.